Normalization is the difference between it trains and it diverges. Pick the right one. By the end, you will clearly see when BatchNorm helps, when LayerNorm wins, and how to test them in a tiny PyTorch experiment. I'm Professor Pi, teaching AI foundations with simple Python. When training deep nets, we often hit exploding or stalled gradients. Normalization fixes internal scale and centers activations so optimization behaves. People reach for BatchNorm for convolutional networks and LayerNorm for transformer blocks. The choice affects stability, speed, and what happens when you change batch size or switch to inference. In practice, this can change convergence or require freezing behavior for fine-tuning. At a high level, normalization recenters and rescales a vector. Imagine a small batch of images. Batch normalization computes statistics across that batch for each channel. Layer normalization computes stats per sample across that sample's features. One looks across samples. The other looks across features. Each wins in different architectures because of how data is correlated across space or across features. We will build a tiny PyTorch testbed that makes a small synthetic batch and applies both normalizers. We will slice batches, flip training and evaluation modes, freeze BatchNorm, and compare channel versus feature behaviors. That way, you can reproduce the exact behaviors and see the failure modes before they hit a larger model. Let's create the minimal testbed and layers. This snippet creates toy data and PyTorch norm layers to set the stage. We seed PyTorch for deterministic tensors, then make a small batch X with 6 features. The object Bn is a BatchNorm 1D that normalizes each feature across the batch, while Ln is a LayerNorm that normalizes per sample across its features. Setting a fine false removes learnable scale and bias, so we focus purely on normalization behavior. The print confirms the input shape and the axes each module will normalize. Now we will probe batch size sensitivity by slicing. This example shows batch size sensitivity using PyTorch BatchNorm and LayerNorm. We run Bn on the full batch and on just 2 samples. Then compare outputs for the same 2 samples taken in different batch contexts. Because BatchNorm uses batch statistics, its outputs shift when the batch composition changes, captured by Bn shift. LayerNorm computes stats per sample, so Ln shift remains near 0 when slicing the batch. A higher Bn shift warns that changing batch size or data mix can change activations even for identical inputs. Next, we will flip training and evaluation modes to inspect behavior at inference. This code contrasts PyTorch training and eval modes, emphasizing BatchNorm running stats. We first call Bn in training mode to use current batch statistics, then switch to eval so Bn uses its accumulated running mean and running var. We compute the average absolute difference between training and eval outputs as Bn eval, which is often non-zero. For LayerNorm, calling Ln in either mode is identical, so Ln eval is 0. This difference matters because mismatched train and inference behavior can surprise you when you switch devices or deployment settings. Now try freezing BatchNorm so it stops depending on the current batch. This snippet freezes BatchNorm in eval mode to remove batch size sensitivity. By keeping Bn in eval, both calls use the same running statistics, so identical inputs produce identical outputs regardless of the batch around them. We compare the first 2 samples processed within a large batch versus alone, reporting Bn frozen shift. When frozen properly, this shift drops near 0, which can stabilize training with small or varying batch sizes. If you adjust momentum, in BatchNorm. Lowering it updates running stats more slowly, more stable, while raising it adapts faster, more volatile. Finally, we will compare the spatial channel case used in CNNs with the token feature case used in transformers. This example contrasts CNN-style BatchNorm 2D with transformer-style LayerNorm in PyTorch. We create image-like data and apply BN2D, which normalizes each channel using batch and spatial statistics. For transformer-like feature vectors, we reuse LN, which normalizes per token across its features. We measure per channel STD for CNN outputs and per sample STD for transformer outputs, both targeting roughly 1. Seeing CNN STD and trans STD near 1.00 reinforces the practical rule. Use BatchNorm for CNNs and LayerNorm for transformer blocks. This toy experiment maps directly to real projects. If you train a small ResNet, BatchNorm is usually the right choice. But watch batch size. If you train a transformer or a model with per token representations, LayerNorm is safer. When fine-tuning with tiny batches, freeze BatchNorm, or prefer LayerNorm to avoid unwanted shifts. What this means in 3 crisp points. It is normalization that recenters and rescales activations to stabilize training. Use BatchNorm for convolutional networks with steady batch statistics, and LayerNorm for per-sample feature stacks like transformers. One caveat: BatchNorm depends on batch composition and running stats, so it can behave differently in training and inference if you are not careful. Next step: tune BatchNorm momentum on the same toy testbed to see how fast running statistics adapt versus how stable outputs become when batch composition changes. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.